Hey, hello everyone. Sorry, I'm by myself right now. Bo is gonna join us really soon. So, um, for now on, I'm just gonna start talking about this topic. Last time, we didn't have a chance to fully discuss what we were thinking about on how to choose a machine learning algorithm and why is this important for your workflow in data science. And we did kind of like a Q&A. Eric and I were doing that. So right now I'm actually gonna discuss some specific topics that I've learned from my experience doing data science, and also what I found that is really helpful out there. I'll be creating an article for Medium after this. I'm gonna try to create a summary of what I'm gonna say here and what Bob gonna say too. And I know you guys will create an amazing summary too, but I'm gonna try to create a specific one. So we've been discussing different topics for data science. And if you remember, the latest data science office hours were about feature engineering, feature selection, how to define a data science problem. We actually talk about data visualization, and these are some of the parts that when you're starting a problem, you need to do them very, very well before thinking on creating a model. So, but before talking about choosing a model for you and your work or what you're doing, we really we should think about what is a model. And we take this definition from science. Right now, we're discussing, like, people in the field, if data science is actually a science. And I think it has some valid points to be a science and some not valid points to be or become a science. But the definition of a model is something we can take from science that is an explanation or a way to represent reality. Okay. And because in science, we're not studying actual reality, we're studying by assuming things. And we are studying reality in a way that we can understand, transform the complex things out there which we are seeing into something simpler, into something that we can actually work with. For example, if you think about gravity, when Newton started his theory on gravity, he really was confused on how he could represent the Earth, because it's a really heavy object with different kind of things, and mountains and lakes and things, people. So what he did for trying to explain the theory of gravity with equations, he thought for like the planet as if it were a simple single point, a single point with only mass. That's it. And the sun too, and everything out there too. Of course, we know this is not true. We know there's a much more complex uh, scenario for what we're seeing as the Earth or the planets. But surprisingly, this way of abstracting reality works. And if you think about it, all of the things that we do in science is this. Of course, it can be more complex. You can go deeper into trying to understand very weird processes or phenomena that are occurring right now. But you need to take assumptions. You need to make assumptions on what you think is behaving, or what is the process behind it that is creating this data. And statistics is actually a branch of mathematics that is doing that all the time. What we're doing in statistics with probability models and distribution is we're trying to think of the process that created this data, because we have the data there. And what we're trying to do is understand the underlying process that created the data. So there comes all the different kind of statistical learning algorithms and models and I don't know, theories that we've come that the human mind created for trying to understand this phenomenon. So this is what we do in data science. Hey, boys here.
Hello.
Hey.
Hello. Are we live already?
Yeah, we're live.
I'm sorry for the delay. So I had my previous appointment went long. So.
All right. I'm just discussing in simple words what is a model in science and what and why we use that in data science too. I just explained how a model is an abstraction of reality that we use making assumptions on what we think the reality behaves. And it's not like the real thing we're studying. We're making assumptions on how things should or may be happening, and then we create a mathematical model behind it. And this is what statistics does all the time. We have data, and what we're doing here is we're trying to understand the underlying process that created the data, and we have to make assumptions to do that.
I love that's how you describe it, because I come from a science background as well, and that's exactly how I think of a model. It's a tool to be used, you know, and I think it's easy if you start off learning about models from a machine learning perspective. It's easy to lose sight of that because you have this massive collection of code that you put in some data and get results back, you know, and that's a lot different than if you're developing like a species dispersion model in biology or developing a model in physics to look at like Brownian motion or something like that. But I think having that mindset is incredibly important when thinking about model selection. Is a model is a tool, and it's something to help you understand the underlying truth of the world, and it's always going to be imperfect to some degree. And you know, so I think that was really well said. So
yeah, thanks. And I gave the examples, the example from Newton's theory of gravity, where he assumes that the Earth and the planets are just points, and we know that's not true, but it works. And where we're doing data science, we need to assume some weird things about the data that is not true, but it will work to represent different kind and I mean, when we think about machine learning, we need to think about representation. What are we representing with our data, and how we can transform the data we have to represent something meaningful for the problem. And this is what we're doing with the model, because it's the same data, just distributed in a different fashion that will uncover the underlying process that created it. And if we discover the process that created the data, we can predict for future data. And this is a model. We have a way of trying to predict or of trying to see the process that created the data. And now that we have that, we can put more data in and try to assume what will happen in the future. And I haven't even talked about any data science model. I was just trying to discuss what a model was.
I think that's really important, and it's something that I think a lot of data scientists don't stop and think about. You know, because especially if you spend a lot of time in software development, you know, a lot of time using a machine learning model is just like using any other library, right?
Very easy.
You know, so it's really easy to use, and that's great. But it's important to stop and think about the science aspect of what you're doing, and you know, why, you know, what assumptions are being made. What are you trying to use this tool for, this model? You know, and I think that's really important.
Yeah. So after that, I think we can go a little deeper into actually to the actual models we use in data science. And but before that, we need to talk about the no free lunch theorem. I don't know if you heard about that, but the no free lunch theorem in machine learning in data science says that there's not a perfect model that will fit every problem. And there is not, I mean, and every problem cannot be solved with the same algorithm. That means that if you have a set of, if you have some data and for some reason the best model was a random forest model with this kind of parameters, that doesn't mean that if you have similar data, that model will be exactly the same model will solve, will be the optimal solution for that. So that will lead us to think that we need to try different models, and you need to try a lot. And some people say that they spend 80% of their time cleaning data, and that's true. But you actually need to spend a lot of time trying and training models, to understand what you're doing, to understand the different hidden features of the data, because every model will give different information about the data. And when you have all this zoo of model tested, then you can decide what you want. And we will discuss that after, like the accuracy and recall and everything like that. But first, you need to remember that you need to try different kind of models, and also have a baseline. When we talk about this with Eric, and last data science office hours, we were talking about the importance of having something to compare your model with, because there are a lot of big like companies, and that have a simple rule to solve a problem, and that rule can be a query, or just a minus or a plus something grouped by in Excel, and that's the baseline. And this is when, if you work for a company, you'll see that they have a lot of these things, and sometimes they assume that the average is the best, or the median is the best, or the mean of this variable is the best for predicting. And of course, we know that we can do better than that, but you need to start by thinking about a baseline. I don't know about in your work as a data scientist, if you can discuss more, how can you create a baseline before even thinking about going into model selection?
So, that's a really great topic. And actually, on my last call, we were talking about that. I was talking through that with the client about what's your baseline, and and it's really important. And I think there's a number of reasons that you've touched on why you want to do that. One, just as an aside, it's hard for business people to really understand what data scientists do often. And if you have a baseline and then you have your result to compare against that, you can show that there was some meaningful difference. And I think the best place to start, and it depends on the type of organization you're in, is to find out what logic are they currently using to make the decision that your model is going to do. How are they currently arriving at that decision? Likely it's hopefully something better than a coin flip, that they're using to make a decision. I just worked on a project where they had this really complex 4,000 lines of SQL code and this 2 massive Excel sheets with a bunch of macros to make some sort of decision. And I can compare the accuracy of that decision as kind of a baseline. And I think that's really important. And I think, when you're, the first thing to ask when you're thinking about what model to use, how it comes down to what is it going to be used for. So like you said, models are tools, they're abstraction of truth. Typically, I found that there's there's a continuum of models. There's models where accuracy is really needed, and it doesn't matter necessarily to know how the model's making the decisions that it is. It might be something that sits in production and just fires off decisions, or like an image recognition model or something. It's not important that a user, even the business, knows how it's making its decision. It just needs to be right. And then there's the other end of the spectrum, which I've run into a lot in life sciences and medical industry, is that how the decision is being made and explainability of the model is incredibly important. The FDA still heavily prefers logistic regression because that's what they know. And so if you're working with pharmaceutical companies and other things like that, you need to keep that in mind, that you might have some highly predictive machine learning or deep learning method, but if that can't help them get through the FDA, then that's the wrong model choice. And so I've found that there's often, I ask really important question is to understand the business. What are you using this model for? What is the purpose of it? Do you want to know what's going on, or do you want to have high accuracy? And and there's ways to get both, depending on the method. But it's often important to know that. Like if your CEO wants to be able to look and see why the decision was being made, then you probably want to use something more explainable than.
Yeah, and I think that is very true, and it comes to the beginning of the workflow in data science, and this is why we discussed this as the first topic for data science office hours, and on how to understand the business is really important, and why, and also how to define a problem in data science. Asking the right questions is very important, because that's very true. If you go, I was working in a bank before, and they needed some explanation for risk management. That was, there were people that their only job is to look at the model and see if they understand it, and explain there's like a full PDF explaining the decision for every model. So you cannot go there and say, hey, I just trained a 72 hidden layer deep learning algorithm and is 99% accurate for predicting, but I have no idea how it's working. Of course, maybe that's great for the business because it will maybe lose less money if you do that, but if they don't understand it, they will not accept it. So in the beginning of every data science workflow, you need to understand what are the restrictions for your model, what can and what can you cannot do first, and that will eliminate a lot of work, because there's a lot of people that are trying to do every new model and thing for their company, and when they finish, they see, hey, but this cannot be implemented because our system is not I don't know, this streaming algorithm cannot be run in our system, or this model is not easy to understand, so it cannot be put into production. So think about that before starting. And when you mention accuracy, I think this is a way of trying to understand which model is the best for your problem. But I think we need to step backward and understand the problem you're trying to solve. And I think we should discuss the different types of machine learning algorithms out there, and maybe we can classify them in maybe 3 broad spectra, like supervised model, unsupervised models, and reinforcement learning models. Of course, there's different kinds of classification, but this is a good one. So I think the same process that will guide, or the same process should end in a way or a question that you'll understand if this question will be answered in a classified way, in a regression way, in a supervised or unsupervised way, and which are the restrictions for this model. So, but what do you do when you start talking with a client and after you understand what they want and the restrictions? And sometimes it's very easy to understand this is something like a classifying model 0 or 1, but sometimes not that easy to see the underlying problem behind an idea of the of a client. So how you go through the process of transforming that idea of the client into a type of machine learning model?
So I think that's a good point, because often there are multiple ways that you can answer a problem. And even with machine learning, for some types of problems, you could structure it as a classification problem, or you could structure it as a regression problem, and it's the same data. You know, it just so I think what I start with is, how are they going to use it? You know, and even, you know, and it helps to see what their outcome is that they're currently predicting, and their outcome may be a continuous variable. But if I find out that they're using some sort of threshold and they're effectively turning that continuous variable into a binary, then that might affect the type of model that I want to use. Instead of predicting continuous output, I might say, you know, you're really using a binary outcome. And a lot of times clients don't think about their data in that way, and that might confuse them to use those sort of terms. But you need to be thinking about, you know, what is the outcome and how are they going to use this? And based on that, what tools do I have at my disposal? You know, if I have categorical outcomes that I want to predict, then there's a number of models that can do that. If I don't have outcomes at all, then there's a whole class of algorithms there. You know, if you're trying to predict some sort of continuous variable, or in the case where this is frequent in the medical domain, where you have a survival model where you're trying to predict a binary outcome and a duration. So you have two outputs. And so, you know, it starts with understanding what they're trying to answer, and being creative about, sometimes it's useful to structure it in two ways of, okay, this is how I could do it as a continuous outcome, and this is at a regression, and this is how I could frame the same problem in a different way. And then, you know, you mentioned competing models. You can compare both of those approaches.
Yeah, and that's very important to understand from the beginning of the workflow, or you will be lost, and or maybe worse, then you'll maybe, I mean, if your team is not agile, and in the end there's some kind of presentation and the client is like, yeah, but this is not what I wanted. This is not what I wanted to predict, and that's like the worst case scenario there for a team in data science, because two things: you lost your time, and the client is not satisfied. So that's just the worst thing. So so after you have an idea, and you have a clear set, if your problem is a classification problem, a regression problem, and or so it could be a supervised problem, or maybe it's an unsupervised problem. So we should discuss one topic, that is accuracy. That some people think that the only way you can present results for your client or your company is 98% accurate, and sometimes that's not needed. All right, you need to think about that. Sometimes approximations are just fine. And you need to explain your company, and this is something that happened to me before, that a model in machine learning is not the truth. It's a representation of the truth. So they don't, and make that clear from the beginning of the project, because if they think that there's gonna be a model for 100% prediction or 100% accuracy, that's not going to be a thing. And if that's a thing, maybe you're overfitting your model. So before just thinking about choosing a model, And in these specific areas of machine learning, think about the accuracy that you want to achieve, and also about training time, because sometimes you don't have the time to have a super incredible accuracy to train all of these different kind of things that will take maybe days or more. So you'll need to understand the timeline for a project before trying to just go there and solve everything. And I think as the page from Microsoft that I think is amazing. I don't know if you guys saw it, but just go there and read all of that page on how to choose a machine learning model. I think it's an amazing description, and they discuss how accuracy and training time is very close. I mean, those are very close variables that you need to think about.
Mm-hmm.
And you need to explain to the business that this model won't predict 100% all of the classes or things. So how would you go there into a meeting with a client, well, and talk about this model won't predict 100% of the truth for this problem?
So I think this is where having the baseline comes in. That can be useful, and say we're doing better. You can explain that there's always noise and variance in real world data, and that there's going to be some inaccuracy. But I've found it helpful sometimes to translate accuracy in terms of what the value means for the business. So, for example, let's say a 5% increase in accuracy actually represents $100,000 of savings for the business, or something like that. That kind of number, is something that resonates a lot more with business than just throwing up an accuracy number. And another point is accuracy statistics by themselves. I think just like one observation alone is dangerous to rely on. Just relying on accuracy alone can be dangerous as well. Looking at precision and recall, or sensitivity and specificity, as they're often called in the medical domain, are incredibly important, because you may have a model that to predict, if someone has cancer, and it may have 80% accuracy, but you go and look at it and it's catching every single person who actually had cancer. And there's some false positives in there, but that's a good model because you didn't miss anyone who had the risk of cancer. Even though it's only 80% accurate, you'd rather falsely predict on some people who don't end up having cancer instead of miss the people who do. So that often tells a lot better story about what is actually going on. And I think when you're presenting, translating it into, okay, what does this actually mean? That we have this actually, or this means in production that we would have caught everyone who had cancer, or that we would have saved this amount of money if we made this risk prediction. That's a great way to explain without focusing too much on, we still have 5% more accuracy to go to get to 100. So, and if the person has any math background, I like to explain that it's like an asymptote. Usually that getting to 100%, it's harder and harder and harder. You get closer and closer and closer, but you usually never quite get there. And if you do get there, there's probably something wrong with your data, or you're overfit.
So I think it's a good point to start talking about something very, very close to the concept of a model. And that's the way that the data is distributed and how an algorithm can find a solution for that. And let me make myself clear. If you're trying to fit a linear model, you're assuming that the variables are will follow a linear linear paradigm, or a linear, I don't know, line. They will be in a line or something like that. And that means, and this is the simplest, the simplest example I can think of. for understanding how a model will assume things for your data. If you
Mhm.
are trying to fit a linear model into a very, very nonlinear process, you will not find anything interesting. And and sometimes if you want to fit a very, very highly nonlinear model into a simple linear data, you will get problems of overfitting the problem, or maybe just making nonsense. And this discussion is about bias and variance and variance. So I found a really amazing discussion on this from the page Elite Elite Data Science that I will post here, and it is called, it's an article called WTF is the bias variance trade-off, and
Mhm.
it's an infographic, and you should all go there and see it. And the key point here is to understand when an algorithm has low variance, and it will be inaccurate on average, but consistent. That means it will fail every time. Okay. uh, and if an algorithm has high variance and low bias, it will be very accurate but inconsistent. That will mean that in one different kind of, in for the data, you will find sometimes that 100 people have cancer with a 98% accuracy, and in the same thing you will find that 3 people have cancer with 98% accuracy. So that's not meaningful. So inside of that, and there are ways, and you should find a way, or trying to find an algorithm that will capture a half and half, or a balance trade-off between bias and variance. For some
So
people, yeah, sorry.
I was going to say, I like that trade-off, and what you just described is a really strong case for ensemble models,
Yeah.
right? Because the idea behind ensemble modeling is that you're not going to have one algorithm that's going to capture all of the variance in your population. So you use a bunch of weak learners that either build off of one another or work it in parallel to capture that amount of variance. So I think that's one reason why like random forest or gradient boosting, extreme gradient boosting are so powerful, is that they deal with that trade-off by building a lot of models and boosting or bagging them together. You have downsides with that potentially, with explainability and production time and other things like that. But that's kind of the why ensemble models are so powerful, is because they deal with that by using multiple models.
And Bo, I think you mentioned something really interesting, and in the last phrases, when you were talking about the false positive and false negatives.
Mm-hmm.
And I think you need to understand which one of those is more important for the business, because sometimes they will be fine with some false negatives, but sometimes they could maybe kill someone,
Mm-hmm.
right? So you need to understand before just going, because that is a trade-off too. Sometimes some models will have more false positives and more false negatives, and you need to understand which is better for the business. And this is something very different, and that takes data science one step forward from just normal science, because sometimes you don't think what's better for the star, or what's better for the planet, and in a model, or what's better for this object moving in a particle, or a particle. But here, when you're solving business problems, you need to understand first the business and what the business cares about. And if a business is working with trying to to have the less amount possible of false negatives, this is where you need to take your hours and your work to try
Mhm.
to make that number as lower as possible. So I don't know if you can mention something, because I think that that's very common in biology and this kind of different uh, uh, areas for data science. And I think you've worked with some kind of this area. So maybe you can say more about your experience there.
Yeah. So in relation to that, about knowing you know about what model to use and what to focus on, I sometimes tell my students that any problem that they're working on has more variables than just are in the data, right? So you have the variables that are in the data, or the features that are in the data, but you also have variables related to the business, to what software tech stacks are you using, what are the needs of the business. Those are all variables that you have to consider when you're choosing an algorithm, not just the actual data itself. And that's why just doing Kaggle competitions might not prepare you for real world data science, because data science is an applied science. It functions inside of a business. And the data is not the only consideration. It's very much important, of how it fits and works with the business. And that's, software developers usually are good about thinking about that type of thing. And so it's good, I think, some data scientists to learn a little bit about software development, and to think about a model. Well, I can get a super accurate model, but how long will it take in production to make the prediction? And
So
that's a really
you will
important
say,
consideration. So if it's
yeah, of
something
course,
that an app
and
that
so you will say that that was one of the I think we're cutting because I can hear you and then I hear you. Sorry, were you talking?
okay, no, go ahead.
Oh, sorry. No, what I was saying is that thing you just said about how these kind of competitions are great for learning concepts and maybe tools, but maybe they're not be they won't be the best for actually preparing for the real world. Maybe this was one of the things that made you create method of data science.
Yes, it is, and I don't know if you want to talk about that now, but I'm going to have an update soon for everyone. But I think, um, in general, there's so much information now out there for everyone who wants to become a data science. There's all kinds of courses you can take, great blog articles that you can read. Fabio produces an amazing blog article like every other day.
Thanks.
And there's so much information, and the biggest thing that I think people lack is actual real world experience. And so method is a way that, that I want to help people gain experience. And the first thing that I'll be launching in a couple days when I have time to finish the website, is something called the Method Data Science Community. And it's like a membership or a club or something that you can apply to have a membership. It's for new data scientists and senior data scientists, who've already taken a couple of courses, who've got some of the technical skill, but want more experience. And it'll be a community where we learn together, and our focus will be doing things to help give back to the community. So, helping on projects like Optimus, contributing to code repositories, to writing blog articles, to teaching people about data scientists, to doing volunteer data science work for nonprofits and governments, things like that. And it'll be a structured way that you can be part of a team that will work on things that actually give back to the community. And I think that's so much. In my mind, that's what people need. Most data scientists don't need another course to teach them how to get a job. They have all the technical skills. They just need experience. They need stuff on their resume. They need that to get their foot in the door. They need networking. And so I would say before you go sign up for some course to show you how to get a job, you probably just need more experience. And so that's what I'm trying to address with Method, and I'd love any of you to be a part of it. I'm hoping, I have a lot going on, as I think all of us do. I'm hoping to get the website launched soon.
Yeah, I think we all of us is. I mean, I think all of the people I see on LinkedIn are just massive, heavily working all the time. I think it's true for me, but I think this is such a fun space and such a fun career to choose right now. That I mean, I never get bored here in data science, and for some of the reasons is this topic we're discussing right now, like trying to understand which model is the best. That can take you weeks for a problem. So it's not like a really, I mean, and I think that's something that will different that makes us different from BI and business understanding in a classical way, because if you go there and ask those guys that are great, by the way, not saying anything bad about them, they had some specific ways for solving problems. And oh yeah, we have a fraud detection problem. Yeah, I have that recipe here. So they will go there to the recipe, they'll read it, they'll maybe program it, or maybe don't program it. They will work that on SaaS or this kind of the big industries with big tools, and that's it. And that worked for maybe 20 years. And I think we need to understand that right now we're in a different area. Data science is trying to get out there and be better at actually understanding both the business and how to improve models, more advanced analytics, and these kind of different things. And this is one of the difference of business intelligence and data science. We don't have recipes here. Of course, we do some things on a daily basis, but the no free lunch theory will guide us to the way of thinking that there's not a specific recipe for every problem in data science. And this is where experience will help you, because you want.
Hello? Oh, I think, let's see, I think Fabio just cut out. Okay, you just cut out, but I think you're back.
I'm back. Yeah, sorry. So
no problem.
What I was saying was, when I was studying data science, and I mentioned this in my blog about how I got my job as a data scientist. I was trained by Coursera and these big amazing courses to have the data there and just run different kind of algorithms, and that's it. And this is not my real life. This is not what I do. I mean, I don't wake up every day and go to my work, sit on a computer, have the data in front of me, and then I run 6 different machine learning algorithms. This is not the work of a data scientist.
What? You had me fooled.
And I mean, we have to do a lot more than that. A lot more than that. I mean, the machine learning part, of course, not easy. Of course, it will take time, but I think is a step that is highly. Maybe people think that this is the only thing we do, and I spend so much time in business meetings trying to understand the business, going out there to read white papers of the business I'm working there, talk to the IT people, talk to the marketing people, and try to understand the needs of the business, trying to transform all of these kind of different ideas into to what do they actually want to solve. And then in the end of this this time, I can just sit in my computer and just try different kind of models. But I mean, it's not true that all we do is just go there, download a data set, and just play with it. And this is something that I think the gap exists in exists from studying data science and actually doing data science.
Absolutely. I completely agree with that. And just to give some perspective of the last 3 months of what I've been working on in my current job, I've had to develop a matching algorithm from scratch that would perform joins between two disparate data sets that don't have a common key. So I had to come up with an algorithm that would produce the best match between those, and that's a really fun kind of problem for me because it's inventing. But that ultimately is a data science problem, but it's not something you can use a recipe for. So I had to come up with a methodology from scratch to do that. I had to produce a dashboard that was taking an analysis that one of the analysts did over a year ago. I mentioned it earlier with the 4,000 lines of SQL code and the 2 massive Excel files. So that analysis would take them, I think, 4 or 5 hours to run to get a result. And I had to produce a dashboard, re-implement it in a new language that could get the same results and apply a whole bunch of other filters in a matter of seconds. And so that is part software engineering, but also understanding the underlying algorithms and methods that they're doing. That definitely is data science. And then I have another project I'm working on that is more traditional machine learning, where we're trying to predict an outcome from a data set. And that's a lot of there's a lot of data exploration and model tuning, other things like that. But especially in a company of the size I'm in, every project is not just, you have a clean data set, let's apply a bunch of machine learning models to it. Yeah. You have to have the flexibility, and I think that's what really makes a data scientist. I'm all in favor for the full stack data scientist, to have the flexibility to not just know about machine learning, but to really address the data needs of an organization. And you may not be an expert in database structures, but you need to know how to use them and access data and know the right questions. And, you may not be an expert in front end kind of UI, BI stuff, but, if you're a good data scientist, you'll at least not be scared when you have something that comes up with that, that you need an interactive plot or something that you won't, that won't be unfamiliar to you. And I think that's, data science is a lot more than just model tuning. It all fits together.
Yeah, and I think that's something very important, because not being afraid of challenges is not easy. Because when we're starting in a new area, maybe you come from a different area, or maybe you're just graduating, and of course you will be scared in the beginning, because there's a lot of information to get, and every day people are making articles and blogs and videos and courses, and it's like overwhelming. It's like, where should I start? And of course it will maybe be overwhelming, but think about that these tools are there for you to use. So when I'm working and I need to do, as you said, an interactive plot in Python, I don't go by my mind and, oh yeah, I remember that. No, I mean, there's a Stack Overflow, there's Google, there are a lot of courses out there, there are books, and what is important here is that you have a goal in mind, but the softwares and the software and the tools for you to use, they may be hard in the beginning, but when you go there and see all of these different kind of tutorials that are out there, and YouTube videos and blogs and articles and full courses on this, you'll see that this is not for a way of, I mean, this is not for you to feel overwhelmed, but calmed. That when you have something in mind, you will be able to create it with the help of the community. And this is something very important about software creation, because this is why Stack Overflow exists, because no one understands. I mean, I don't think that 90% of people that are working with software are an expert in a language, or they can create a book on C++. I don't think that's true. What I think is that we are all in a community of software people that are trying to help each other with the things we learn from someone else. And that's it. Because when I mean, this is why I create blogs. this is my way of giving back, because when I was starting in data science, when I was starting in understanding Python and R and all of these different kind of tools, these kind of articles were my life. I spent days reading articles and watching videos and doing all these different kind of courses. And this is why I feel my responsibility right now is try to pass that information to more people. And I think this is why this discussion is happening right now. This is our way of giving back to the community.
Absolutely. I echo that. I love data science. I love learning about it. It's something that's been constant since I first heard about it, and I even jumped professions to come back to it. But I firmly believe that most of the problems that we encounter may seem intimidating at first, but you can figure it out. You can solve hard problems. There's so many resources out there, and most often it's just a case of becoming familiar with something, and that might take some time. But once you're familiar with it, you'll look back and say, oh, why was that so hard?
Yeah.
But it's just, the nice thing about working with programming languages is that by definition, programming languages have to be based on logic, right? Because that's how computers work. And so once you learn that, okay, there's a way of doing things, it's just learning the language. And so I really like that about programming, is that I know that it's most cases it's something that's knowable, that I can ultimately figure out if I put in the time and ask the right questions.
So I think we have a question here that will guide the discussion I was thinking of for the end of the session.
Okay.
And is, would you say that EDA or exploratory data analysis helps pointing to the right option of a machine learning algorithm to use, at least at the beginning? This is by Christian Willig. So I think thinking about EDA in data science, I mean, we've discussed that in the past sessions, but when you're thinking about creating a model, I think this will help you with one thing, is understanding your features. So remember that you could have a problem that will have maybe 1,000 different kind of features. For a machine learning algorithm, that will translate into dimensions, all right? And there are ways of transforming these different kind of dimensions into simple or maybe less dimensions that will describe all of your data. So feature engineering, feature selection, those are ways for maybe before just going out there and trying machine learning algorithms, you should do a very, very exquisite job on choosing the right variables for your problem, understanding them, creating new ones, and selecting the ones that are important for your model. And when you go there and you see and you think, okay, I just use these different kind of approaches for maybe creating different kind of model of variables. I select the best ones and everything like that. Something very important to think about when you're doing a machine learning model is the number of parameters you're trying to fit. So when you translate our definition that we gave in the beginning of a model like an abstraction of reality, that will mean mathematics. That's it. It's math, and every machine learning algorithm and deep learning algorithm is just math. All right, and in that algorithm there are parameters to be fit, and this is what you do. When I say fit here, I mean, when I was studying this, it was really weird for me because I didn't understand the word fit. And when I saw this scikit-learn um, uh, API, I was like, why should I fit here? And what does it mean to fit a random forest? Because maybe it is easier to think about fitting a line into a linear distribution, but how are you fitting a tree to a thing? So when you think about fit, think about we are setting the best values for the parameters. Okay, and when we discuss about accuracy and training time, this will be important too, because if you don't have the power to find the best values with for your data, because you don't have enough data, because you don't have enough hardware capabilities, you need to think of models that are maybe not the best, but they are an approximate solution for what you're trying to do. And this is why a lot of people right now think that deep learning is everything and you should use it for every problem out there, and that's not true, because sometimes just a logistic regression that you only need to fit 5 parameters there, and or 3 parameters, is very easy, and it is not very heavy for a computation, and you can train that in maybe seconds or minutes, and maybe you will get a good accuracy. Maybe it's not a deep learning standard, but it's better to have something than nothing.
So and we can close on this. I think that's a really good point. And I'm a biologist by training, evolutionary biologist, and this concept, that you've described is true in biology, that often the species that survive are the ones that do something good enough. They don't need to be perfect. They just need to be good enough. And biology is full of examples with that. And that's a good reminder for me of that, sometimes not to say that you should strive for mediocrity or not doing your best, but everything's about trade-offs, and sometimes good enough is, that itself is an art, to know when is it worth it to spend more time on a problem, and when is it not worth it, and when is your result good enough and you can move on to the next thing. And I think that's a really important skill to have.
Yeah. So I think we have time to we have time for one question. Is it better for beginners to learn more about the stats that is needed in data science, or what exactly better to start with? What do you say?
This is hard question for me to answer, because I started with stats. So I don't know that that's better or worse. I know people that have come from a software perspective and learned the stats after. And that's why I think, and I've advocated this a number of times in the past, that learning how to solve problems is the best approach for me to learn what I need to know. But that being said, I think that having basic understanding of stats is really important at some point in your career, and there's ways to do that. One reason I love R as a programming language is that you can learn R while you're learning statistics. That's in fact, my favorite stats class that I took was a graduate level stats class, and everything was in R. And I learned R and I learned the stats really well because R is a statistical programming language. And so that's if you can do both at the same time, that's really great.
Yeah, and that's good advice. Maybe if you don't know anything about stats and you don't know anything about programming, you should learn R. Mm-hmm. Maybe that's a way of killing two birds with one shot.
Yep.
So I think we can just end it here. I will say that we didn't have time to cover more specific topics that maybe just more like a high level discussion on this, or so detailed that are not worth taking more time on this. Maybe we'll go to another direction in the next data science office hours. But as I said in the beginning of the video, I will be creating an article about this. So I will maybe mention more things that we didn't have time to cover here, and I think I'll have that by next week. I hope, and I will just go there and also write all of these different kinds of I think references I mentioned here. So thanks a lot for joining us. I hope you liked it.
Thank you,
Thanks, Belle,
everyone.
for being here.
Yep, we have the two dynamic duo today, missing
Yeah.
everyone else. So, all right. Thank you, Fabio.
All right, everyone. Yeah, thank you guys. Bye bye.
See ya.